How do wheels help a wagon coast? The answer to that question is that wheels eliminate sliding friction between the wagon and the ground. I worded that answer carefully because wheels eliminate only sliding friction, and even then, they only eliminate sliding friction between the wagon and the ground. Those details are important, and my goal for this video is to explain why. When you're trying to move a wagon down the sidewalk, you want it to be able to coast indefinitely. In other words, you want to avoid wasting any energy, and you want to avoid wearing out the wagon and the sidewalk. Since those two problems are associated only with sliding friction, that's what you want to avoid. Sliding friction. Static friction isn't necessarily a problem, so long as it doesn't prevent the wagon from moving on the sidewalk. One solution to this problem, that is, one way to get rid of sliding friction between the wagon and the sidewalk, allowing the wagon to coast and not wasting any energy or wearing anything out, is to use rollers. So let's start with that approach. So before we put in wheels, let's put in rollers. If I sit the wagon not directly on the sidewalk, but on these metal rods, watch what happens. All of a sudden, it can coast perfectly. Wow. I haven't eliminated friction altogether, but I have eliminated sliding friction. Those rollers are doing what I call touch and release in terms of their contact to both the sidewalk and the wagon. By touch and release, to show you, let me get a larger roller. As I roll this beverage can along the sidewalk, it's landing on the sidewalk, it drops itself onto the sidewalk and then lifting off, touch and release. At no time does it ever skid or slide across the surface. So there's no sliding friction there, but there is static friction. So at any given moment, if I grab the can and try to scoot it along the surface, I'm now being opposed by the forces of static friction between the sidewalk and the can. They're fighting me. And up to a certain point, they will continue to do that until finally I overwhelm them and cause the can to skid or slide. But as long as those forces are small, static friction remains, and so the can rolls. And it rolls along that surface without wasting any energy and without wearing out the can surface or the sidewalk surface. Similarly, the same thing can go on for the wagon. I can roll the wagon on that beverage can, and the can is touching and releasing the bottom of the wagon. Only static friction. Well, the can's too big for this little activity, and the rollers, as I've got them, are better, but they are now doing touch and release to both the sidewalk and to the bottom of the wagon, and they're allowing the wagon to move perfectly, that is, to coast perfectly, because there's no energy being wasted. The rollers are experiencing static friction and nothing else. Static friction is actually a good thing for rollers. Without it, there would be no tendency for the rollers to move with the wagon. For example, I have the wagon here at rest on rollers that are at rest. And if I move the wagon abruptly to your right and there's no static friction, the wagon will just leave the rollers behind. They're inertial, after all, so they don't accelerate with the wagon. With static friction, that is specifically between the bottom of the wagon and the top of the rollers do undergo an acceleration to the right as the wagon undergoes an acceleration to the right, and they move to some extent with the wagon. I say to some extent because the rollers don't accelerate as fast as the wagon does. They actually travel at half the speed of the wagon. And that's sort of a geometry thought problem, that those rollers are interacting not just with the moving wagon bottom, but they're also interacting with the motionless sidewalk top. And they average the two velocities, the velocity of the moving wagon and the velocity of the motionless sidewalk. So they travel not as fast as the wagon, not as slow as the sidewalk. They travel halfway in between. And that's a problem for rollers. They don't keep up with the wagon. They travel at half the wagon's speed and roll out from behind the wagon. If you want to use rollers with a wagon, you can do it, and you will waste essentially zero energy. Rollers are perfect. Within the limits of the imperfect world, rollers experience no sliding friction, waste no energy, cause no wear. They're great, except they shoot out the back all the time. So you need 3 rollers at a minimum, and you have to keep replacing rollers. Every time one roller shoots out the back, you have another one to put in front, and you can keep recycling them over and over. As you roll it along, you have to just keep on moving a roller from the back of the wagon to the front of the wagon, back of the wagon to the front of the wagon, and so on. Well, this is kind of a nuisance even for a wagon, and it's certainly a problem in an automobile traveling 60 miles an hour down the highway. If you want to be cycling rollers from the back of your car to the front of your car at 60 miles an hour on the highway, more power to you. Not a great solution. A better solution is to go to wheels. And so I'm going to get rid of the rollers and the wagon that has no wheels and switch to a wagon with wheels. I have the luxury of 2 wagons. Woohoo! And this wagon now, because it's on wheels, takes its rolling surfaces with it. The bottoms of those wheels are still doing the touch and release trick I mentioned earlier. They land and leave, touch and release, and they experience essentially no sliding friction, just static friction. That's great. There's no rubbing, no wasted energy down here at the bottom surfaces of the wheels, and there's no wear, in principle, at the bottom surface of the wheels and the top of the pavement, the top of that sidewalk. This is a great solution. Is there any problem at all? Yes, there's still sliding friction around. Where? The sliding friction is hiding from view. It's not between the wheels and the pavement or the sidewalk. It's in what's known as the hub of the wheel. Where the wheel attaches to the wagon is a portion of the wheel known as the hub, and it's suspended in an axle so that the axle passes through the hub, and in that little area where the axle sits and the hub grabs it, they're rubbing. There is sliding going on as the wheel turns. If the wheel still experiences sliding friction in its hub and axle, what's the point of wheels? It turns out that the consequences of that sliding friction between the hub and the axle are much less than the consequences of sliding friction between either the wheel and the pavement or the bottom of the wagon and the pavement. That's a matter of work and energy. The diameter of the axle is very small, and so its circumference is small, which means that every full rotation of the wheel only slides the hub across the axle a short distance. It's sliding against the force of sliding friction, so this is wasted energy. But since the distance is small, the work done against sliding friction is small. So yes, a rotating wheel on a fixed axle does waste energy because of sliding friction, but not very much. And the narrower that axle is and the smaller the hub, the less energy is wasted. That's good as long as the axle can tolerate, you can use a narrow enough axle and still tolerate both the wear and the weight of the wagon. And there's some compromise made then between making the axle so skinny that it wastes almost no energy but it breaks or wears out, and making it so fat that it never wears out but it causes a lot of energy waste. Well, another helping thing here is to add axle grease between the hub and the axle. It's called axle grease for a reason. It's a lubricant that sits between the motionless axle and the turning hub and tries to reduce sliding friction and the wear that occurs and the energy waste that occurs. It's time for a question about wheels, but I'm going to ask that question in a context that is very different from wagons and bicycles and automobiles. After all, Wheels and wheel-like components are common in the objects around us, including objects that don't use their wheels to travel from place to place. The context for my question is mechanical timekeepers, such as this antique carriage clock and this modern mechanical wristwatch. Mechanical clocks and wristwatches contain many wheel-like components, and those wheels, I'll just call them wheels, are suspended in tiny polished axles that rotate in tiny polished cups that are made from jewels like ruby and sapphire. We can actually see those in this watch. We'll take a close look at how this watch is operating, and you'll be able to see its tiny little rubies. So my question then is this: why does that suspension technique, namely tiny polished axles rotating in tiny polished jewel cups, allow the rotating components in one of these mechanical timekeepers to waste almost no energy and work consistently for years? As the axle turns in its tiny jeweled cup, it does slide across the cup surface and therefore does experience sliding friction. However, the distance traveled by that tiny, narrow little axle as a wheel-like component rotates, the distance is very small, and therefore the work done against the force of sliding friction is minuscule. Remember, work is the product of force times the distance traveled in the direction of that force. And although the sliding frictional force is there, the distance traveled by the axle against that sliding frictional force is very, very small. So the wheel-like component wastes very little energy. Moreover, the axle, which is typically a polished piece of metal, and the cup, which is a polished jewel, that pairing has a very small coefficient of friction. Unlike rubber on pavement, for example, metal on ruby or sapphire has a small coefficient of friction. Finally, the two polished surfaces, the jewel and this polished piece of metal, they're so smooth that they don't have serious collision problems as they slide across each other, and they experience almost zero wear. Therefore, this wheel-like component can go round and round and round for years, decades, or even centuries with almost zero wear. And that's why one of these clocks or watches can keep on ticking for a very long time. But there's actually a better solution to this friction problem in the hub axle system. The solution is to insert a bearing between the axle and the hub. And that bearing is our old friend, the roller. Instead of loose rollers, where have I put them? The loose rollers, we put the rollers in a loop and mount them to form what's known as a roller bearing. It consists of a bunch of rollers very loosely held in a frame known as a cage, and we insert this. We put it on the axle like that, and into the hub, which I don't have here, but the hub would grab this on the outside, and it's the rollers again. They do touch and release as the wheel turns around the fixed axle. Those rollers do touch and release both on the axle and on the inside of the wheel's hub, and there's no sliding at all, and therefore no energy wasted at all. What's more, the rollers travel all the way around the axle and they recycle automatically. So roller bearings and their cousin ball bearings, where the roller is replaced by just a round sphere of metal or some other hard substance, they cycle perfectly, they roll, pure static friction, they waste no energy. And so our world basically runs on bearings like this, things that turn typically have these inserted to get rid of even the small sliding friction that would otherwise appear between an axle and a hub. Here's another roller bearing with a built-in hub. There are the rollers sitting in the hub, and if you insert an axle in here and turn the axle, the rollers go round and round. Only static friction, no sliding. This is a ball bearing. It has a hub and it has a cylinder to hold the axle in the middle. And as you turn the axle, the balls roll. And I know it's a ball bearing because this guy can be rotated so that you can actually see the balls. There they are. Those are the balls that roll between the outer cylinder and the inner cylinder and ensure that there is no sliding friction, just static friction as the balls touch and release. Alas, my little wagon doesn't have any fancy bearings between its wheel hubs and its axles. And that's why, as I roll the wagon back and forth, it does a lot of squeaking. That's sliding friction between the wheels and the axles and other components of the wagon, and I could probably get rid of that with a little bit of oil or grease. Another day. Before I leave this wagon, though, I want to talk a little bit about the type of wheel it uses. It uses what's known as a free wheel, a wheel that turns essentially freely and that the wagon doesn't try to control. The wagon doesn't exert torques on the wheel deliberately to make the wheel spin. So what makes the wheels spin? It turns out that the source of the torque that causes the wheels to begin rotating, to undergo angular acceleration, is static friction between the bottom of the wheels and the top of the sidewalk. When the wagon is just motionless on the sidewalk, its wheels are motionless. They're not translating and they're not rotating. Everything's totally at rest. But if I pull the wagon to your right, the wheels begin to rotate. And they rotate because static friction, astatic friction force from the pavement on the wheel pushes the bottom of the wheel to your left. That force is there because the static friction is trying to prevent the wheel from skidding on the sidewalk. Let me go back here. If the wheel skids on the sidewalk, like I'll hold it and drag it, well, static friction doesn't like this. Actually, it becomes sliding friction. So static friction is trying to prevent that sliding process. And it does that by trying to keep the bottom of the wheel at the same velocity as the top of the sidewalk, namely 0. So as the wagon accelerates to your right, the sidewalk exerts a leftward static frictional force on the bottom of the wheel to keep the bottom of the wheel motionless. And that force exerted at a lever arm from the center of rotation of the wheel, namely the middle of the axle, produces a torque on the wheel and causes the wheel to undergo angular acceleration. So, it's a little bit of a complicated story, but as I pull the wagon to the right and cause the wagon to undergo normal acceleration, static friction from the pavement, the sidewalk, exerts a leftward frictional force of static friction on the bottom of the wheel that produces a torque on the wheel that causes the wheel to undergo angular acceleration. And that angular acceleration is toward me, away from you, and the wheel begins to spin. Free wheels turn because of static friction, but not all wheels are free wheels. The rear wheel of your bicycle turns because you're pedaling the bicycle. And it's called a powered wheel because you're providing it with power. Powered wheels are the focus of the next video.